Hello, hello, and welcome to the next concept in voltaic cells, which is the copper zinc cell, which is also known as the Daniell cell. So it's a very, very common kind of voltaic cell that has a consistent energy output. Now, the reason why we're focusing on this one right now is to add a little bit more detail about the design of these voltaic cells. And I'll remind you of a few things as we go through this to make sure some of the stuff from the previous podcast has actually sunk in. First thing is I want you to notice that the direction of the electron flow has already been indicated on here. That's what these arrows this way show. Now remember something that I said. Electrons always flow in a predictable manner in a voltaic cell. And no exception, electrons are going to flow from anode to the cathode. And that gives us a huge hint as to which electrode is which here. Now, have a look. If electrons are flowing from zinc to copper, then that means zinc has got to be our anode. And vice versa, they flow from the anode, of course, over here to our said cathode. Now, consider what's occurring then. If our zinc is the anode, then that's where oxidation is happening. If that's where oxidation is occurring, then that means that the zinc solid, notice the direction of this arrow, this is important, is turning into zinc ion. How does it do that? By losing electrons. This is oxidation, right? So you can imagine that there would be 2 electrons lost for every 1 zinc 2 plus ion that is formed. Right? So the zinc solid is turning into the zinc ion. The opposite is true at the cathode. The cathode is where reduction takes place. So in this case, the copper 2 plus is gaining 2 electrons and turning into copper solid, right? Consider the logic of this. One of them, the anode, loses the electrons. The other one, the cathode, gains the electrons that were lost. Hence, this is based upon a set redox reaction. All right, let's keep clarifying this. Now, in this scenario, we have a situation where, just to kind of give you a blow up of what's happening, right? Look at this, where, like I said, our zinc metal is turning into zinc ion. And like we talked about over on this side, the copper ion is going to be turning into copper solid. Now think about observations that would come from this, right? Consider what would actually be seen. Literally, if you were to take the mass of the zinc electrode before you start the reaction and then take the mass of the copper electrode afterwards, the zinc solid is going to go down in mass because it's being reacted, and vice versa. The copper solid is going to go up in mass because the copper ions are reacting out of solution into copper solid. Similar type thing then, if you consider this solution, that bright blue color that is characteristic of copper 2 plus ions is going to start to fade, right? Because the copper 2 plus is being reacted away. It's decreasing in concentration. One more thing I want to call your attention to in here is that chloride, right, which is an anion, is flowing towards the anode in a salt bridge. And vice versa, potassium K plus ion, the cation, is flowing towards the cathode. Don't lose sight that that's what happens. A little bit of a misnomer in this diagram. The voltmeter wouldn't read 0. There would be a voltage going through. That's just to show, hey, here's a voltmeter attached. Okay, let's keep going. This is just clarifying, same thing, this is in your notes, right? In terms of the direction of flow in those anode versus cathode, right? That the zinc loses the electrons versus the copper 2 plus gains them. This is all in your notes. Have a look at it again. Make sure it's making sense. The next thing in terms of stuff that needs to be written in is understanding the half reactions that are happening at the cathode and the half reaction happening at the anode, right? Don't lose sight of these. Cathode is always going to be a reduction reaction with a gain in electrons. Anode is always going to be an oxidation reaction with a loss of electrons. Vice versa, that means that the cathode is going to be your SOA and the anode is going to be your SRA. Don't lose sight of those, please. We're going to need to use our table on page 7 to be able to figure that out for each individual situation. Now, in terms of how we get the net cell reaction, well, that's the same thing we did before with getting the redox reaction. And essentially, for an accurate redox reaction, we need to make sure that the electrons going in are balanced with the electrons going out. In this case, they are, which I can then add the two reactions together with my balanced electrons being canceled out. There's our net cell reaction. This part, folks, is the same as what you did in the last couple of weeks. Alrighty, let's keep going here to just a diagram about observations again. This is something else that you're going to have to talk about for voltaic cells that you're analyzing. What would you expect to see? And I hinted at that already, but here's a blow up of the actual zinc anode, an actual copper cathode that would have been in a voltaic cell with the zinc and copper. And you can see how much the zinc has eroded away as that solid zinc turns into zinc ion. And vice versa, you can see how copper has built up on the original copper electrode. And that's pure copper, okay? Remember too, I talked about that blue color fading away as the copper 2+ turns into copper solid. Let's put this into practice. Here's an example that you have in your notes that's totally not filled in, but you can imagine you're going to get similar questions to this on your assignment. Now, there's a few things that you really have to catch that are hard to see when you first look at it. This is all the information that you're given about this voltaic cell, that it's aluminum iron. And you have to be able to deduct from that, hey, this means that we actually have an aluminum half cell that's present, and we have an iron half cell that's present that's making that full voltaic cell, which consider then your first step is going to have to be that you list out all the chemicals present so you can pick out, hey, this is the SOA according to the table on page 7, and this is the SRA according to the table on page 7. Now, like I said, keep in mind, half cells. So, of course, aluminum solid is present, but it's not just aluminum solid that's there. The metal is in its corresponding ion in solution. So even though it doesn't mention the Al3+, you have to put it in there. It is one of the options in terms of chemicals available. Same thing for the iron. The iron, of course, we have iron solid that's there, that's mentioned, but we also would have the most common iron ion present, which is Fe2+. Now, there's a couple things you can do if it's not obvious to you that that would be Fe2+. What I recommend is when you're looking at your table here is find yourself where iron is at, right? So here's iron. And there's your hint. Once you find iron that you know is present because it's mentioned, then you know it has to be in a solution with Fe2+. Okay, so use that as your hint. If one part of the half reaction is present, the other part, the Fe2+, has to be present as well. Okay, so that's listed. The last one, because these are all solution, don't lose sight of, is water is there. Okay, now, again, going back to here, we would look for the SOA and the SRA. So starting way at the top, if we start building our way down, you would actually find that this, the Fe2+, is your strongest oxidizing agent. And vice versa, when we start from the bottom down here for the SRA and move our way up, you're going to find that it's aluminum. That is our SRA. Still a spontaneous reaction. SOA is above the SRA. But consider that. It's not both metals that are the SOA and the SRA. It is actually the metal ion of Fe2+ that acts as the SOA. And it is the aluminum solid that acts as the SRA. Okay, next step then is logical, same as what you would have done before, label them. Aluminum solid is the SRA, Vice versa, Fe2 plus is the SOA. Okay. Second step, guys, that we'll start to get into on the next page there, but you better figure out what reactions are actually happening, right? So figure out the oxidation reaction of the SRA and figure out the reduction reaction of the SOA, because from that, you're going to have to build this. Oxidation happens at the anode, right? Reduction happens at the cathode. This is how we're going to build and start our first part that we actually have to do for the question. Sketch a complete diagram of the apparatus. Include your arrows to represent both electron flow and ion movement. There's an awful lot that needs to be included in one of these diagrams. It is important that everything is there. I'll show you exactly what I want on the next slide here. Okay, check it out. So here is number 1, drawing your diagram. And get used to actually drawing these without having a template in front of you. Ultimately, what you need is to start by drawing one beaker and then the other beaker that would be beside it. And that's kind of logical. The next thing is, without exception, we always need a salt bridge that's going to be connecting those two beakers together. And we need an electrode in my 1/2 cell, an electrode in the other 1/2 cell. Add the electrolyte that all of this is going to be sitting in. And we have to have, connecting the two, a wire to make sure that we have a complete circuit essentially. Okay, I tend to start usually, it's not a hard and fast rule, but I usually put my anode to the left and then I'll put my cathode over here to the right. Now, how do you decide what the anode and the cathode are? Well, that's what we were figuring out in that previous slide, right? So, for example, here, my SRA, right, is undergoing oxidation at the anode. Oh, so that means that you would have to take this and label this as aluminum. Sorry, my writing is messy on this iPad here. Aluminum solid is your anode. Same thing. Your cathode is where the strongest oxidizing agent is and where reduction is occurring. So we can't label Fe2 plus as an electrode. Electrodes have to be solid conductors. So that means the corresponding solid, Fe solid, is what is the actual cathode. All right. Next thing you need to label is the ions that would be present in the electrolyte. So it'd be Al3 plus with my anode and Fe2 plus with my cathode. You have to show always the flow of electrons, which again, no exception. Electrons are always going to flow from the anode to the cathode, okay? You also have to show the flow of the ions, and you don't know what inert electrolyte is in the salt bridge, but you do know that the anions are going to flow to the anode and the cations that are in here are going to flow to the cathode. We're very close to being done. The last step that you have to show is how things are changing. Now, don't forget, aluminum is undergoing oxidation, which means it is losing electrons, which means, well, that's a funny looking arrow. Wow. Let's try that again. See if I can draw it straighter. Well, not much. Anyway, aluminum solid is going to turn into aluminum ion as it loses electrons. Vice versa, make sure your arrows go the right way. The Fe2 plus is going to turn into iron solid as it gains electrons. If you struggle with that last little bit, you might find it easier to do those last red arrows that I just put in. This one here and this one. After you do the half reactions. It might be a little bit more obvious then. Okay, let's move on to the next part of the question. Number 2 is asking you to write out the appropriate half reactions and the net cell reaction. Guys, this is just like what you used to do. Write down the oxidation reaction, write down the reduction reaction, write out the redox reaction. We're just calling it half reactions and net cell reaction now. Okay, so here we go. Number 2, slightly different in how we do this now then. We're going to say, okay, what's happening at the cathode, right? Now, again, don't lose sight The cathode is just a reduction reaction, and it's the SOA. So same stuff that we did before. This is going to be your iron, your Fe2+, to be specific, which is going to gain 2 electrons, right? It's reduction, which is going to turn it into Fe solid. Now remember what I said. You might find it easier to write this half reaction before you show how iron is moving from Fe2+ to Fe solid. That becomes a little more obvious in this half reaction now that you can see which one is going to which. Anyway, moving on to the anode. The anode is going to be an oxidation reaction, which is the strongest reducing agent, which means going through this is our aluminum. So aluminum solid is going to lose electrons to become Al3+ plus 3 electrons. Now take note, our electrons are not balanced. We have 2 going in and 3 going out. This goes back to what you had to do in previous lessons. I need them to balance out, which means I'm going to multiply the cathode's reaction by 3 and the anode's reactions by 2. That way I'll have 6 electrons gained and 6 electrons lost. You're ready to do what's called the net cell reaction, which again, like I mentioned, is just the exact same thing as your redox reactions you did before. Okay, remember now we have 3 Fe2+ aqueous plus 2 aluminum solids, which will produce 3 iron solid plus 2 aluminum 3+ aqueous. In terms of observations, well, consider what's happening. Use your logic. For example, notice aluminum solid is changing into aluminum ion. That means that the aluminum anode is going to decrease in mass. Make sure you look at the notes in terms of how I wrote these observations. Vice versa, consider what iron is doing. Iron 2+, I wrote down the wrong charge there. 2+. Iron 2+ is changing into iron solid. So that means that the iron cathode is going to increase in mass as it changes from ion into solid metal. You'll also notice a bit of a color change. If you check out page 11, guys, I'm going to refer to this quite a bit because it's got so much in ions colors in it. Our Fe2+ is a noticeably lime green color. And as that Fe2+ reacts out of solution as it gains electrons to become iron solid, that lime green color is going to decrease. It's going to become less intense, if you will. All right, so that there is all 3 of the questions that you were asked, including listing the observations that you would expect to see during the operation of the cell. Now, you guys are now set that you can do a decent chunk of the questions now. So have a look. You should check out number 1, but please, please, please leave out D. Okay, you're not ready to do that one yet. 2, 3, and 4 are completely review. So these are questions that you could have answered from last week's stuff, but it's important for us to keep those skills feeling good as we continue on with the unit. As always, let me know if you've got questions. Have a great rest of your day, guys. Hope all is well.